So I'm going to talk about single replacement reactions this time. And the general formula, like I gave a couple days ago of a single replacement, is where you have a substance A, and it's going to react with BC. What's going to happen is A then is going to go with C, and B is going to be left all by itself. Now, how these work is you're going to use something called the activity series to predict what the products are going to be. So I'm going to give you an example of a single replacement reaction where lithium, and it'll be a solid, is going to react with copper sulfate, CuSO4, and that's going to be aqueous, dissolved in water. And what I'm going to get out of that is lithium sulfate, Li2SO4, which is going to be aqueous, and copper, which will be a solid because it's elemental copper. All right? So why does this work? Why did A kick off B to then go to this new compound AC and be all by itself? Well, the reason why it works is something called the activity series. And I'll show you what the activity series looks like. It's this right here. And it has to do with reduction potentials and stuff that you do with batteries and electrochemistry, but this is the first start of it. Now, if you look at it, lithium is a really highly reactive element. Down at the bottom, gold is really a non-reactive element. If you're lucky, you'll find gold in your backyard because gold doesn't react with many things at all, and it can be found in nature just as pure gold. Lithium is far too reactive. Lithium is always bound up with something in some form of mineral. So you're not going to find lithium because lithium is a really, really reactive metal. In terms of what a reactive metal is, that's a metal that is going to give up its electrons. You might all of a sudden, start thinking, well, gosh, I've kind of heard about lithium lately because people are making batteries out of lithium. And the reason for making batteries out of lithium is the same reason that I just explained lithium being at the top of the activity chart, is because lithium wants to give up electrons, making it usable for batteries. So looking at this reaction that I just did, lithium, okay, was the lone element. It was the A. Okay? What lithium was trying to replace was copper, which is down here. Now, since A is higher than B, and B in that case was copper, okay, A was the lithium, A is going to bump it out of that position and replace it. So that's what you're looking for. So whenever the lone element, the one that we've sort of designated as this A, is higher than the one it's replacing on this activity chart, the reaction is going to happen. If A is lower than B, there would be no reaction. So looking back at this equation, okay, because lithium right here was higher than the copper, okay, lithium was higher than the copper, the reaction took place. So it's really easy to predict single replacement reactions as long as you have have that activity chart. Okay, so let's just say let's say I'm making another hypothetical single replacement reaction, and in this case I'm going to take I'm going to put iron. Let's say I have Fe, and it's a solid. Okay, and I'm going to react it with sodium nitrate, NO3, and that's aqueous. All right, and now I want to figure out what I'm going to get. Well, like with all single replacement reactions, what I'm looking for is if the iron is going to kick off the sodium. So what do? I go back to the activity chart and I find iron. Okay, so right there's the iron. And then I find sodium, which is right there. Well, sodium is more active than the iron. And so iron is not able to replace the sodium in that reaction. Because sodium is higher than iron, there will be no reaction. So you would just say no reaction. Okay? Won't happen. Nothing will happen. They'll just sit there and look at each other.